Hello everyone, welcome back to our final video on the alternating series test. So I'm going to show just a couple more examples. I'm actually going to do this last example right here, and then I'm going to put 4 examples and let you guys practice them, and then I'm going to just show the work for all of them and make sure that you got the answer correct and briefly talk about them. So this was actually telling us to show that this series is a conditionally convergent series. And so right up here at the very top it says if the absolute value of our series does not converge, then the alternating version does, then the series will conditionally converge. So one of the things that I actually have not talked about yet in this entire series of videos is the actual absolute value part of this, why we were able to go and look at our series and see if it's conditional or absolute. So I'm going to actually talk about that a little bit in this exact video. But before we do that, we're going to assume that this is an alternating series. And when I mean assume, I mean that we would actually go through the variables. The one, and you'll see that we plug this in, it's going to change signs, positive, negative, positive, negative. So when I keep saying assume, we have actually verified that it actually is an alternating series. So what we're going to look at now is we're looking at the absolute value of this, right? Which just basically means that this is going to go away. And so we're just looking at a sub n. So when I actually ask us to meet the 2 conditions that we need to do, we're just looking at the a sub n. So the first condition is the term 1 over 3 to the n plus 1, is that greater than 1 over 3 to the n plus 1 plus 1? And so you guys can clearly see that if I were again to cross multiply, I get 3n plus, now this would be 3n plus 3 plus 1 plus 4, is that greater than 3n plus 1? And again, since n is positive, then we know that we add 4 to a number plus 1 to a number. This is always going to be greater, so we know that this condition is actually met. And so our second condition, just to assume that our series will converge, right? Our series will converge, we're going to look at the limit as n approaches infinity of our a sub n, or the absolute value of our a sub n's, which again would get rid of this right here. And so we're just looking at 1 over 3n plus 1. And we know right now that this obviously is going to equal 0, right? Because it's bottom heavy. And so we know that it is going to converge, right? So I know that the first part, we know it's going to converge. We know that this right here is going to converge. So I'm going to go ahead and write that at the bottom of our page here. Now, we want to look at whether or not it actually will conditionally or absolutely converge. It's already told us what the answer is, but let's just show you what it is. So when we do take the absolute value of this function, then what we're really left with is just 1 over 3n plus 1, right? And so this is what we want to look at. And so we now know from the direct comparison test that this series, we can actually look at just the harmonic series 1 over 3n. And we can actually pull out the 1/3 and just look at 1 over n. And since we know that this is a harmonic series, we know that since this series right here is going to diverge, then I know that from the direct comparison test that this series right here is also going to diverge. Therefore, I can say that even though we converge here, our function is going to be a conditional convergent problem. Okay? So do the test to see if it converges or diverges. Again, we did an example where the limit was not 0. We know that it automatically diverges because the nth term test tells us that's going to be the case. So if both these things hold true, we know it at least converges. And then we look at just the absolute value of our series, which basically just looks at just this piece right here. And then we can say, okay, well, does this converge or diverge? If it converges, then it's an absolute. If it diverges, it's a conditional. All right? So here's what I want to do. So moving on for 1 second, what I was just saying right here holds it very true, that if my actual series converges, right, if this converges, then so does the series a sub n, right? So we just kind of talked about that a little bit of time. So, and this would be an absolute convergence problem. So what I'd like to do is show you guys these 4 examples, and I'm going to let you just take a second, pause the videos, do them on your own, see whether or not it converges absolutely, conditionally, or diverges, and then I'm going to come back on and have the answers written for each one individually, talk about it for a second, let you do the next one, and then this little guy right here, this is the one I've been talking about in all 3 videos so far, and we'll get to that in a little bit of time, but this is a special example. So I'd say take a second, pause the video, and see if you can do question number 9, and I'll be back with you in a second with this solution written out and see if you're okay with it. So go ahead and pause the video and try number 9. Okay guys, here is the answer to question number 9. We wanted to check to see, first of all, if it was an alternating series. We plugged in 1, 2, 3, 4, 5. The series actually changes sign, so we know that it's the alternating series. So once that's the case, we want to make sure that our 2 conditions are met for the series to converge. So the first one is that the previous term must be greater than the next term. So the first term must be greater than the second term. We check that out. We've done this many times to see that that's true. We also want to make sure that the limit as n approaches infinity of just a sub n, right, just a sub n, is equal to 0. And so I rewrote this as 1 over the square root of n is 1 over n to the 1/2. It's a bottom-heavy function, so it's equal to 0. And so once we've done that, we now know that this actually converges. And then in order to find out if it conditionally or absolutely converges, we have to look at the actual series, the a sub n, right? We have to look at this series right here. And so when we do this, it's 1 over n to the 1/2. This series will diverge because it's the p series. Therefore, since it does pass the alternating series test, but a sub n will diverge, we can say that this will conditionally converge. Okay, so hopefully that's good with that. Now let's see if you guys can do question number 10 and question number 11. So go ahead and pause the video and do both those examples, and I'll come back with those answers. Alright guys, I went ahead and put up the answers for number 10 and number 11. For question number 10, we could see that, again, it's an alternating series. I've done this many times before, so we looked at the 2 conditions for the alternating series, and it passed both of those completely fine. So I knew that it converges, and so then all I had to do here was look at the series of a sub n, and so I went ahead and rewrote it down here. And through the direct comparison test, I knew that this series here is very similar to the 1 over 3 n squared, and since I know that this is a p-series test, through the p-series test, I was able to find that this actually converges. So since it passes the alternating series test and it actually converges, then I can say that this series right here, converges absolutely. And then for question number 11, I apologize if the writing's hard to see here, but I immediately look at the limit. I think that the limit's the easiest thing to see for this problem. So if I see this, I can see the limit as n approaches infinity of 2 n squared, and I just realized my limit is completely wrong. Completely wrong here. My limit, 2n squared minus 1 over 1n squared is actually equal to -2, not -1/2, -2. Since this limit does not equal 0, then I can say that the series will diverge by the nth term divergence test, or it also fails the alternating series test. So there we go for those 2 examples. So the last example that we're going to look at in this problem set is question number 12, and this one's actually a little tricky, and to save a little bit of time here, so if you plug in n equals 1 to this problem, you're going to see that this is going to give you a positive 1, right, so it's going to be positive 1, times cosine of 1 pi, which is 1 pi, all over 1. Well, that's just going to give you -1 times 1. So the first term is actually going to be equal to -1. Well, then if we plug in n equals 2, we're going to get -1, right? Because it's going to be 2 plus 1 is -3, or positive 3. And it's going to be cosine of 2 pi all over 2. Well, that's going to be -1 times 1 over 2, right? Because this gives you a positive 1. So it's going to be -1/2. And then for our last example here, we're going to get n equals 3. And n equals 3 is going to give you a positive 1, and it's going to be cosine of 3 pi over 3. Well, this is going to equal 1 times, well, this is actually -1 over 3, which is going to give you a negative 1/3. So you can see for this exact example, this is not an alternating series. So what must I do? Mimic through the comparison test. Through the direct comparison test, it's going to mimic a harmonic series, right? Because this is always going to be a number. As you guys can see, it's always 1 or negative 1. And this is going to be over n. So this is going to diverge. So we can now say that this series is going to also diverge, right? This is going to diverge. So the series is going to diverge. And we can say it's going to diverge by direct comparison test. The next thing I want to show you guys is the alternating series error. So I will see you guys in the next video for that.